everything came from. Despite the fact that it does make sense of a ton about the early universe, it's hard for different models, like roundabout or bouncing cosmologies, to explain where the universe came from in the first place. These models say that the world goes through cycles of getting bigger and smaller, but they can't get around the issue of a beginning. What really does nothing mean? What did the universe come from, assuming that we accept it had a beginning? It's not as simple as it seems to ponder nothingness. Quantum fields are still there, even in the emptiest parts of space. Even when there are no particles or energy in these fields, they still move and carry energy. So, what is closest to nothing is still something. A vacuum brimming with quantum potential. The vacuum origin hypothesis is the idea that the universe could have started from a quantum fluctuation in this vacuum. It has intrigued physicists for quite some time. This hypothesis suggests that the world began as a change in nothing, which made everything we see today. Although this is still just a theory, it's a fascinating idea that makes us think about what life and nothingness truly mean. There are quantum fields and virtual particles. Space isn't the only thing that makes up the universe we see. Quantum field theory states that there are energy fields everywhere in space. These fields combine with each other to make everything, from atoms to stars. These fields are still active even when they have the minimal amount of energy, known as the vacuum state. Virtual particles, brief particles that appear and vanish instantly, are continuously taking energy from the void. These fields and virtual particles are vital to the structure of the world, yet they make it harder for us to grasp what nothingness is. Can we ever truly say that the world was empty if it is full of these moving fields, dark energy, and expanding space? The acceleration of the universe's expansion is caused by dark energy, an unknown force. The early rapid expansion can be explained by inflation. The current expansion, on the other hand, is caused by dark energy. Even far into the future, when all the stars have died out and matter is spread out, dark energy will keep the universe expanding. In this way, the universe has never been truly empty, and it likely never will be. The movement, radiation, and quantum fields that occupy space will continue as long as dark energy is present. Embracing the mystery, scientists have been trying to unravel many mysteries about the early universe for a long time, and inflation theory has transformed how we think about them. Yet, as we've seen, it also makes us consider new questions. What did we have before inflation? What caused it to begin? Also, why does the universe seem to resist the idea of nothingness? We may not have all the answers yet, but the search for them is far from over. We are getting closer to understanding where everything we observe in the universe came from as we continue exploring it and developing our ideas. Be sure to check back for more articles like this one. Let us know your thoughts on these cosmic mysteries below. The enormous detonation was not the genuine beginning. It was more like a change from the state of expansion to the hot, thick world we know today. There are issues with the ginormous detonation theory, the horizon and flatness issues. The theory of how things came to be explains a lot about the world, but it has a few problems. This is known as the horizon problem, which means that parts of the universe that have never been in contact with one another appear to have the same temperature and other properties. This implies that these regions must have been connected to each other before, even though they are too far apart to have shared information since the Big Bang. The flatness problem is another issue. The forces of expansion and gravity appear to be perfectly balanced in the universe, making it flat and stable. But how did the universe maintain this fine balance? The answer is inflation, which explains why space expanded so rapidly that it smoothed out any initial curvatures. Why did our universe have these particular characteristics when it first began? Scientists have pondered this question for a long time. Early theories helped us figure out what happened in the Big Bang, but newer theories, such as inflation theory, explain why the universe is so uniform and why some expected particles, like magnetic monopoles, don't exist. The question of what happened before the Big Bang is still very much open. Alan Guth, a physicist, proposed a new way to explain these puzzles in 1980. Inflation, the early phase of rapid and consistent growth. Guth suggests that the universe's energy wasn't separated into matter and radiation particles like it is now. This energy, instead, was part of space itself and expanded the universe at an astonishing pace. Inflation solves three main problems in cosmology. The horizon problem. It asks why the universe appears to have such a uniform temperature and density when different parts had no time to communicate since the Big Bang. According to inflation, everything was once connected in a small, dense state before it rapidly expanded, which explains why things are so similar now. The flatness problem. Inflation expanded the universe so extensively that any initial shape or curvature was smoothed out, making the universe look incredibly flat. The monopole problem. Inflation also explains why we don't see strange relics like magnetic monopoles, which should have appeared if the universe had gotten too hot. Inflation prevented the universe from reaching those extremes, so these relics didn't form. Inflation not only addresses these issues in cosmology but also provides insight into how objects in space, like galaxies, came to be. Small quantum fluctuations in the fabric of space were amplified to cosmic scales during inflation, creating the bumps that would eventually grow into galaxies, clusters, and stars. The cosmic microwave background, CMB, the glow from the Big Bang, and the large-scale structure of the universe have all shown that these early imperfections were real. During the 1980s, scientists made precise predictions about how these changes would appear in the CMB, and many observations since then have confirmed those predictions. This strengthens the theory of inflation as an explanation for how the universe began. But inflation also raises an important question. If inflation explains what happened before the Big Bang, does that mean the Big Bang wasn't the true beginning? In the original Big Bang model, the universe could be traced back to a singularity, a point where temperature and density were both infinite. However, inflation complicates things. Because inflation causes space to grow at an extraordinary rate, it would take an infinite amount of time for the universe to reach a state with no size, the singularity the Big Bang model describes. It's hard to imagine the universe starting from a single point, as inflation prevents that from happening. We can see evidence from a very brief time back, such as the marks left by quantum fluctuations, just before inflation triggered the Big Bang. Moreover, eternal inflation complicates things further. In this scenario, inflation never truly ends. It stops in certain regions, like our universe, but continues in others, creating a multiverse, a collection of many pocket universes, each with its own Big Bang. This process erases all records of what might have existed before inflation, making it nearly impossible to determine how the universe began after that point. Eternal inflation and the multiple universes it implies are fascinating, but they don't go back infinitely. Studies have shown that an expanding spacetime cannot extend backward indefinitely. It must have originated from a different, perhaps single, state. This suggests that inflation doesn't always provide a clear answer to the question of where everything began. What was there before the enormous detonation? Researchers have been attempting to answer this inquiry for quite a long time, yet new findings are giving them astounding new data. Brian Cox and other experts have shown that the answer might be a great deal trickier and more unnerving than we thought. Cox says the idea is that the universe wasn't hot and dense before the Big Bang, as we generally think. Rather, it was cold, empty, and growing rapidly. The expansion we're seeing now is called inflation, and it made the universe what it is today. However, inflation didn't happen everywhere. It stopped in certain places, which is what we now call the Big Bang. But it kept going in other areas. This idea, called the inflationary multiverse, suggests that our universe is just one of many. This perspective suggests that the universe resembles a fractal with a perpetual number of Big Bangs occurring in different parts of existence. Each of these regions turns into its own world, and our own is just a small part of a much larger cosmic landscape. But what is inflation, and why did science find it so peculiar? Before the Big Bang, space expanded rapidly, which is called inflation. It was caused by a strange kind of energy. At that time, space spread quickly, making the universe look flat and even by smoothing out any irregularities. Then, the energy that was making space expand was left behind. This warmed up space and created the particles that make up everything around us. We used to believe that the Big Bang, this sudden eruption of energy, was the beginning of everything, but it was only a part of the universe's history. This raises new questions. What did we have before inflation? Also, why does the universe keep getting larger? The universe is never truly empty. The concept of absolute nothingness doesn't really work in space because it is so vast. Even if we removed all energy, new types of energy are continuously created as the universe expands. Even in the absence of particles, photons, and radiation, there are quantum fields, which are the building blocks of reality. This is why space will never be completely empty, and the universe will constantly be producing radiation, even where there is nothing else. True nothingness can't exist because these quantum fields ensure that something always remains. It is also possible that there was nothing before the universe. According to what we know now, space still holds some energy even when it appears empty. This zero-point energy is the closest thing to nothingness we can imagine, yet it still represents something, the minimum amount of energy that exists everywhere. As the universe evolves from the past to the present, it is continuously changing. As space expands, it pulls galaxies farther apart and cools the universe overall. In the beginning, after the Big Bang, the universe was hot and dense, but as time went on, it became larger, colder, and less dense. As space expands, so does the light from distant galaxies, which is why we see redshift, when light waves from galaxies appear to lengthen as they move away from us. This stretching causes energies to drop and temperatures to decrease, making the universe much colder now than it was at the beginning. Even if all matter and energy were removed from the universe, there would still be empty space governed by physical laws and filled with quantum fields. Dark energy is the mysterious force that speeds up the expansion of the universe. This space would continue expanding even if there were no particles or radiation. Inflation played a significant role in shaping the history of the universe. The period of rapid expansion before the Big Bang, called inflation, was essential in shaping our world. Before inflation, there was likely an extremely powerful form of energy in the universe that made space stretch at an incredible speed. This expansion smoothed out any early irregularities, making the universe as smooth and even as it appears today. However, inflation raises new issues. Where did everything begin? If inflation continued indefinitely in certain areas of space and created an endless number of Big Bangs, what role does inflation play in how we think about the Big Bang? To answer these questions, we need to examine three main ideas: the hot Big Bang, the theory of cosmic inflation, and the concept of an ultimate beginning. Independent but connected, the Big Bang and inflation are both key to understanding the universe. Astronomers like Edwin Hubble and Vesto Slipher observed that galaxies were moving away from us in the early 20th century. This led to the idea that the universe is expanding, implying that it must have been much smaller and denser in the past. This idea eventually led to the Big Bang theory, a moment when all matter and radiation were compressed into a single point with an infinitely high temperature and density. However, the Big Bang theory alone couldn't explain certain observations, such as the flatness and uniform temperature of the universe. This is where inflation comes in. It's possible that inflation made the universe so flat and smooth, but it also means